against me.
Let's talk about Newton's law of gravity. So Newton's law of gravity is the force of gravity equals gravity's constant times the big mass times the small mass over the radius squared. So if you have a distance twice as far away, then you will experience a force of gravity 4 times as less. Every object experiences a force of attraction between each other, but like me and this pencil have a force of attraction. It's just so small that we call negligible. Also, large objects actually do have a force that we can feel. There's the Earth and us on it, keeping us grounded. But then there's also the Moon, which has our tides. It attracts our tides. Earth is an oblique spheroid, so it is more squished at the poles and has a smaller radius, and it is elongated along the equator. The North Pole, because it has a smaller radius towards the center of the Earth, has a force stronger than the equator, which in turn gives it an average acceleration of 9.87 meters per second squared. The equator has an average acceleration of 9.77 meters per second squared because it has a longer radius. We'll be talking about objects traveling vertically. So for a spaceship trying to leave Earth's orbit, it will need a stronger acceleration upwards than it will downwards, or at least it will have to equal that to be able to overcome the force of gravity. So it will have to have a force applied more than the force of gravity or equal to. Otherwise it will come crashing back down to Earth. Gravity changes depending on the altitude you are towards or from the center of the Earth. So if we do an example, let's say an astronaut with a mass of 70 kilograms takes off from Earth. He goes 150,000 meters in the air, and so we want to find his acceleration due to gravity at both points A on Earth and B in space. So by using Newton's gravitational law, using gravity's constant times both masses over the radius squared, we can see that on Earth he has an approximate acceleration of 9.8 meters per second squared. And then compare that to 150,000 meters in space. You'll have a larger radius, so that will give you a smaller acceleration. As you can see here, it's 9.34 meters per second compared to 9.8 meters per second squared. So at an altitude you experience less gravity than you would on Earth. Here we're going to talk about gravity on an incline. Because you have a mass on an incline and the force of gravity is always towards the center of the Earth, you're going to have two components of those forces depending on the angle at which it is on. So you'll have a force of gravity perpendicular to the surface, and that magnitude will give you your normal force, and then you can find out your friction. And you'll also be able to find out your force due to gravity parallel towards the surface. So if there's no acting forces on here, the system will accelerate downwards because the force due to gravity won't be as strong as it would be if it was in free fall, but it has a component parallel to the surface that will push it down to the end. We're going to talk about gravity and massless objects. So if we have a photon of light coming from this direction and it's going to make a projected pathway past the planet, it will actually bend around the planet according to Einstein's special relativity principle at an angle, because technically all mass is energy. We can't use Newton's equation, but using special relativity we can confirm that planets will attract energies off their course and pull it towards a planet.